In this section, we'll be examining several other families of word problems and strategies for solving them. It's important as we go through this study, though, to concentrate on the general idea of the method of solution and not just trying to find an answer to this problem or that problem or whatever. You should come away with the idea that you can recall a general concept for attacking the different families of word problems. Now, the first family of word problems we're going to talk about here involve markup and discount. And those problems involve percents and a hidden operation. Now, the notion of markup and discount have to do with retailing. In a retail store, let's say it's a hardware store, and let's say I'm the owner of a hardware store. And I buy things like hammers and lawnmowers, and then I mark them up. I mark up the price in order to sell them and make a profit. So, the selling price is determined by taking the cost of the items and adding some markup. Now, how is the markup figured? That's the idea. That's the trick in these kinds of problems. It turns out that the markup isn't the same amount of money for every different product in the store, and that only makes some sense because, after all, if we buy a hammer from a hammer manufacturer for, let's say, $10, and we mark it up $4 and sell it for $14, okay, that's one idea. The markup was $4 on the hammer. What if we buy a lawnmower for $350? Are we going to mark it up $4? Of course not. It's going to be marked up more than that. And generally, the markup is a percent of the cost. That is, the selling price of an item is determined by or calculated by taking the cost of the item and adding some markup. But the markup is some percent of this cost. So markup is some markup rate, which is a percent, times the cost. Let's look at a problem and we'll see how it all works. A store buys an item for $35. If the markup rate is 40%, what is the selling price? Well, let's see. We understand our general idea here, and this is what we want to grasp in this notion of markup and then later for discount. It's the general idea that selling price is cost plus markup, and the general idea that markup contains a hidden operation. It's the multiplication of some percent times the cost. So this markup is some percent times cost. All right, now we fill into this. Let's see, selling price is cost, $35, plus 40%. Remember the markup rate, 40% or 40 hundredths times the cost of 35. Then performing the indicated operations, 35 plus 14. Now 14 was the 40 hundredths times 35. That is the amount of the markup, you see, and the markup rate is 40%, but the amount of the markup is $14. All right, adding these two, we find that the selling price then would be $49. Here's another one where we're trying to find the markup rate. Let's say some jeans sell for $42. If the cost of the jeans is $16.80, what's the markup rate? Well, let's see. We understand our general idea is that selling price is cost plus markup, and we understand that the markup is some markup rate, a percent, times the cost. We have to bear that in mind. Now, we need a label for what's unknown here, and the markup rate is unknown, so we'll let P stand in for the markup rate. So we've got, let's see, 42 for the selling price, the cost is $16.80 from above, and then the percent, the markup rate is P, and the cost is $16.80. And now we just solve the equation. Subtract $16.80 on both sides, and we'll get this on the left, and the $16.80 disappears on the right. Subtracting here, we get 25.20, or simply 25.2. Really don't need this zero here. If we're talking dollars and cents, yes, I'd say $16.80. But if I'm just talking about decimals here and solving an equation, I really don't need to write that zero, do I? Okay, 25.2 over here, 16.8 over here. I divide on both sides by 16.8. I find P then to be 1.5. Now, I need this to be in the percent form, so I change the decimal to the percent by sliding that decimal 2 places to the right and tacking on a percent sign. So the markup rate is 150%. Let's talk about problems involving a discount. Discount occurs when a store has a sale. The sale price is found by taking the old selling price and then subtracting some amount of discount. But the discount contains a hidden operation. It's some percent of that old list price. Here's what I mean. The sale price, the new selling price, you see, is the old list price minus the discount. But this discount is some percent times the list price. So it's a discount rate, a percent, times the list price. Here's how it works in a problem. It says a CD player is marked down from its list price of $820 to a sale price of $574. What is the discount rate? You begin to solve the problem just by putting down your general idea involving discount problems. And that general idea is sale price is list price minus discount. But you understand that discount contains a hidden operation. It's some percent called the discount rate times the list price. Now all we have to do is write a label for the unknown quantity. The unknown quantity is the discount rate. It's this percent. So we're going to let P stand for the discount rate right up here. Let P stand for the discount rate. I've repeated our general idea, our general concept from below. And discount, remember, is some percent times the list price. And it's important that we write that in because of the replacement idea to make up our equation. So in our next step, the sale price is $574 from the problem, and then the list price is $820. The percent is P that we're looking for. The list price is $820. And we go through and solve the equation. Now first we would subtract $820 on both sides. We'd clear the $820 over here. On the left we would see that we're subtracting the $820. Now, this minus P times 820 can be written like this, or it can be written like this. Either way you write it is fine. A lot of times the convention is to write letters to the right of numbers when we're talking about a kind of a factored form. The listed factors, we put the numerical factors first and the letters last. Anyway, it doesn't really matter though. Subtracting here, we get negative 246. We would divide on both sides by the coefficient of P, whether it's written like this or written like this, and that means we're dividing on both sides by negative 820. When we divide by negative 820 over here, we get the cancellation as expected to give P. When we divide by negative 820 over here, we get this fraction. Dividing here, we find P to be 0.3, and we want this as a percent because we're looking for the discount rate, a percent. So we change 0.3 into the percent by sliding the decimal 2 places over and tacking on a percent sign. The discount rate then is 30%. Another family of word problems is called mixture problems, and we can be mixing any number of different kinds of things in order to have a mixture problem. Here we're mixing some flowers. It says roses cost $1.25 each, carnations cost 75 cents each. An arrangement of 1 dozen flowers cost $11. How many of each type of flower are in the arrangement? Now, it turns out that with mixture problems, a lot of times when you read the problem, it sounds extremely intimidating. You don't have any idea where to start in a problem like this. But generally, you build your mathematical model according to the mixing process itself, according to what is going on and being mixed. And you say to yourself, I'm going to take this thing that's in the mixture, and I'm going to add this other thing in the mixture, and I'm going to set it equal to the whole mixture. That's the idea. And with problems involving money, usually it's value plus value equals total value. So in this problem, we can think about it like this. We can think, well, the value of the roses plus the value of the carnations is equal to total value. Now, how do we figure the value of those roses? Well, it's figured, there's a hidden operation in here. We don't know the value of the roses. We know that one rose has the value $1.25, but we don't know how many roses we have. That's part of what we're looking for. But the value of all of those roses would be the number of roses, however many there are, times the cost of one rose. You see, so it's the number of items times the cost of a single item. And then for the carnations, it's the same idea. It's the number of carnations times the cost of one carnation. And then over here, the total value is given in the problem as $11. So this is $11. Now all we have to do is set some label on the number of roses and the number of carnations. We have this cost given in the problem. All right, let's come up here and talk about that. How do we assign a label to the number of roses and the number of carnations? Well, certainly we can just let a letter like X stand for one of them. That is the number of one of them. I'm going to letting X stand for the number of roses. What about the number of carnations? Do we just select another letter? Well, we haven't talked about equations that involve two letters yet in this textbook, but we can do this. We can write the number of carnations in terms of the number of roses because we know there are a total number of flowers in the arrangement. It's a dozen, you see. So if there are 12 total flowers, then and X of them are roses, then the others, that is 12 minus X, would be the number of carnations. All right, this is a very important step or point in representing unknown quantities in mixture problems. Often you have to do this kind of thing. You have to use this technique. X represents one number of things, and then the total minus X represents the number of another thing. All right. Now, let's go back to this value plus value equals total value. All right, the value for the roses would be the number of roses times the value of each rose. That's $1.25. And then for the carnations, the total value of all the carnations, the number of carnations times the value of each carnation. They were 75 cents a piece. And we're given the total value as $11. And now we solve this equation. Now, another technique, or a technique that's used a lot of times in problems involving mixture is to clear the decimals early on in the solution process. It's part of the simplification of the overall equation. Now, I could clear these decimals by just marching through and multiplying each term by 100. If I multiply here by 100, I would multiply in this factor by 100, and this decimal point would move two places to the right, and I would have 125x. Over here, for this term, I would multiply by 100, and I would elect to multiply that 100 into that factor right there and make this 75, and then 75 times the 12 minus x. You see, that would be the idea. And then this has to be multiplied times 100 as well, so I'd have 1100 on the right. At any rate, using that technique, you can clear decimals in equations very easily. Now, it's not too hard to work this one, though, using the decimals, and here we would have 1.25x, and then let's see, 0.75 times 12 would be 9, and then 0.75 times minus x is minus 0.75x. And then this is equal to 11. Now we would kick the 9 to the other side, collect the x's over here, work the problem. I'm sure we can do that at this point. We would find x to be 4. Now, once you get an answer like this and your mind has been on this part, you might not know what you've gotten for x, but all you have to do is go back to your labels and look at what x stood for. And that's one of the values in writing the labels, is to be able to refer back and know what you've been dealing with. Well, here x is 4, so we know we have that number of roses, so there are 4 roses. And let's see, for the number of carnations, there are 12 minus x carnations. And if x stands for 4, then 12 minus 4, oh, that's 8. So there are 8 carnations. Let's look at a mixture problem involving money. This one says, an inheritance of $40,000 is divided into 2 investments earning 8.5% and 11% interest. How much is in each investment if the total interest for 1 year is $3,550? Now, we're talking about money here, a total amount of money in earned interest for the year. So it should make some sense that we're talking about money plus money is total money, because we're given the information about total money for the whole year. Okay, so it's interest plus interest is total interest. So we think about it like this. The interest at 8.5% plus the interest at 11% is equal to the total interest. Now let's jump further into the problem and figure out how do we calculate interest. Well, we know from before that interest is percent times rate times time, PRT. So this is some PRT, and this is some PRT. And the total interest is given as $35.50. Now what about this PRT, principal times rate times time? The principal is the amount of money invested at a certain rate. So we're going to need a label for this. Well, let's call this P, let's just call it X. And the rate is given here as 8.5% or 8.5%. When we change it to decimal form, this decimal slides 2 places over, so it's 0.085. The time is 1 year, so we really don't need to add a 1 as a factor out here. All right, now here's the trick in this problem is to represent the principal invested at 11%. If we know the total amount invested is $40,000, that's the total inheritance, and we know that X number of dollars is invested at 8.5%, then the money left over is invested at 11%. And that money left over is what we represent by taking the total amount of money and subtracting X. So it would be $40,000 minus X as the principal invested at 11%. All right, so this amount of interest is principal times its rate, 11%, times time understood 1, equals $35.50. And now, once again, we could use this technique of clearing the decimals by multiplying by 10 or 100 or 1,000 or whatever value like that would cause the decimal points to slide enough places to the right to where we're dealing with whole numbers. Now, since we have 0.085 here, we need that decimal point to slide 3 places to the right. So we would need to multiply by 1,000. Multiply by 1,000 here, and we would get 85x. Multiply by 1,000 here, I would multiply that 1,000 into the decimal factor, you see, and the decimal would slide 3 places over, so I would have 110, you see, and then that would need to be multiplied times each of these two in the next step. And then over here, I have to multiply by 1,000 as well, so I just tack on 3 zeros and go about the business of solving. Now, once we solve this in a few steps, we find X to be 30,000. And we look back, and I didn't write the labels here because I'm just kind of setting up the problem and overviewing it, but the X stood for the amount of principal invested at 8.5%. So we have $30,000 invested at 8.5% interest. And the remaining money is invested at 11%. Now the remaining money it was 40,000 minus X. That means 40,000 minus 30,000. So there would be $10,000 invested at 11% interest. Here's a third kind of mixture problem. This is a really classic kind of mixture problem when you're actually mixing liquids. It says, how many liters of 60% salt solution must be mixed with 10 liters of 20% salt solution to get a mixture that is 30% salt? You see, so we're mixing things together, and as mentioned before, although we're talking about different kinds of things, we're talking about flours, we're talking about money, we're talking about liquid mixture, the mathematical model is formed by emulating the mixing process. I mean, we really can think about here, we're talking about taking some liquid that's maybe in a beaker. You see, you can actively think about it like this. We have some liquid, and we're going to mix some other liquid. And when we pour those two beakers together, it's some total amount of liquid. Now, what do we have involved here? Well, we have some quantity in each of these beakers, and there is a percent of salt in them. So it's a quantity and percent. Now, the percent, let's see, we have how many liters of 60% salt? So this beaker, let's say, has 60% salt. And we don't know how many liters are in here. And then we're mixing with that, well, let's see, must be mixed with 10 liters of 20% salt. So this liquid is 20% salt, and it's 10 liters. Now, what's on the other side of the equation is the result of this mixture, you see, and that's what we want to represent over here. And we want the mixture to be 30% salt. So the result will be 30% salt. Now, my question is, how much stuff do we have? How much liquid do we have? And often that's the trick in dealing with liquid mixture types of problems. How much stuff do we have over here? We're not told in the problem. Now, in the other mixture problems, we were told the total. We had a total amount of money involved in those flowers before. It was $11. We had a total interest earned for the inheritance. It was $3,550. But here, we're not told the total amount of salt involved. We're just told that the result is a mixture that has 30% salt. But how many liters are there? Well, we can tell by looking at the liter labels for the other two items in the mixing process. We have X liters here. We have 10 liters here. So the total is going to be X plus 10. So X plus 10 liters will be the result of this mixing process. Now, actually in this, really what we're doing is we're calculating the amount of salt in here. We have X number of liters, and 60% of that mixture, 60% of that liquid is salt. So when we take 60% of X, we have the total amount of salt that we have here, a quantity of salt. And here, 20% of 10 liters, 20% of 10, that's going to be 2. So we have 2 liters of salt right in here, you see. So that's the idea. We're really saying salt plus salt equals total salt. We're not going to think about it like that. The way you think about these things is it's some percent times quantity plus percent times quantity is equal to the resulting percent times total quantity. That's the idea. Percent times quantity, resulting percent times total quantity. Okay, so our equation looks like this. It's 60% or 0.60 times X, or just X, I don't need the parenthesis here, plus 20% times quantity is equal to the resulting percent times the total quantity. And then we would go through again and solve this. And as was the case before, we can either use the decimals here, work this through using the decimals, or we can clear the decimals by multiplying through, actually by just 10 here. If we multiply by 10, all of these decimals slide over 1, and we're dealing with whole numbers, and it's a little bit easier. Anyway, at the end of this problem, we find out that X is equal to, I think it's 3 1/3 liters. And we would look back at our labeling. Oh, it was X stood for the number of liters of the 60% salt solution that needs to be mixed with this other stuff to get the result. So it's 3 1/3 liters of that 60% salt solution.
50 gallons of 70% acid solution are obtained by mixing an 80% solution with a 50% solution. How many gallons of each solution must be used to obtain the desired mixture? Now it turns out that we build an equation from a verbal model which is emulated by the mixing process itself. That is, if we can imagine these two liquids being mixed together, we're really building a verbal model and therefore building an equation. Now notice if we take some 80% acid and some 50% acid, mix them together, which is what this problem is saying, what we get as a result is 50 gallons of liquid, which is 70% acid. So now if we put that idea into equation form, that is, some liquid plus another liquid is equal to 50 gallons of 70% acid, then we're building our verbal model. All right, if we let X stand for the number of gallons of that first container of liquid, then the next container of liquid can be represented, the number of gallons can be represented as 50 minus X. Now that's important, to represent the number of gallons in the second container correctly. Well, now let's indicate the percent acid involved in the two solutions being mixed. We know from earlier that 80% acid was in one container and 50% acid was in the other container. Now it turns out that our equation is based upon the amount of acid involved in each of these containers. That is, the amount of pure acid in the first container plus the amount of pure acid in the second one is equal to the total amount of pure acid. And that amount of acid is found by multiplying some number of gallons times the percent of acid. Now that's true in every case here. Now notice that gallons times percent plus the gallons times percent is equal to the total gallons times the resulting percent. And that's the way we build our equation. So here's our verbal model, and here comes our equation. X number of gallons times 80% plus 50 minus X number of gallons times 50% is equal to 50 gallons times 70%. And all of this is from the information below the equation. Well, let's go on to solve the equation. Now, what we're going to do next is write 100 times each of the terms here. Now, notice I'm doing this in order to clear the decimals. If I simply multiply 100 times each of those percents or each of those decimals, it'll simply slide the decimal points 2 places to the right, and now we can deal with whole numbers instead of the decimals. Well, let's continue. X times 80 is 80x. 50 times 50 minus x is 2500 minus 50x. And on the right, 50 times 70 is 3500. Of course, we'll want to collect the x's on the left and throw our constants to the right. And when we do that simplification, we find that 30x is equal to 1000. Dividing on both sides by 30, we find x to be 33.3. Now remember that x represented the number of gallons of the 80% acid solution. And in the other container, we represented the number of gallons by 50 minus x. Well, x in this case we just found to be 33.3. So 50 minus 33.3 is 16.7. Now we can write our solutions. We know that 33.3 gallons of the 80% acid solution and 16.7 gallons of the 50% acid solution are needed.
Let's turn our attention now to problems involving distance, rate, and time. Here's one that uses the formula rather directly. It says if you ride your bike at an average rate of 18 kilometers per hour, how long will it take you to ride 30 kilometers? As soon as you see a problem involving distance, rate, and time like this, you just write the formula down. That is, instead of thinking about some magical mathematical model for solution, a formula becomes our mathematical model for solution. So we just write down distance equals rate times time and fill in the information. Well, let's see, we're told the rate is 18 kilometers. All right, so R is replaced with 18. How long will it take you to ride 30 kilometers? That's a distance. So 30 goes in place of distance, and time is unknown. And away we go. We divide on both sides by 18, so we get 30 over 18 is equal to time. Now we reduce the fraction. Let's see, 6 goes into both of these. 6 into 30 goes 5, and 6 into 18 goes 3. So 5/3 equals time. Gee, what does this mean? 5/3 equals time? Well, we can identify the unit of time pretty easily by looking at the rate. There's a relationship now between all of the values that appear in problems such as this. If the distance is in miles, then the rate is in miles per some unit of time. If the distance is in feet and the time is in seconds, then the rate will be in feet per second. You see, so there has to be that correspondence among the units given. All right, here we're told that the rate was 18 kilometers per hour, so the time then is some number of hours. So this is 5/3 hours. Now 5/3 is 1 2/3, so this is 1 2/3 hours. And we can change this to hours and minutes because it's 1 hour, 1 whole hour, and then 2/3 of an hour. Well, that's 2/3 of 60 minutes. You see, we can take 2/3 of 60 and get 40. So this is 1 hour and 40 minutes. Now, this is a very straightforward kind of problem, and it just uses the formula directly. Just pop in the formula, plug in information, grind out an answer. That's pretty easy. The more intimidating kinds of problems in this family of problems occur when either two vehicles are involved or two directions of travel are involved. We might have one vehicle like a canoe that goes upstream and downstream. So that's one vehicle but two directions of travel. On the other hand, we might have two different vehicles involved. We'll take some examples in a minute, but let me kind of outline what we're going to do with this, our general strategy with it. We know that distance is rate times time, and we're using this formula. When two vehicles or two directions of travel are involved, we're going to set up a table of information to help us structure our equation for solution. Now, we're looking for a condition. It may be evident just in reading the problem that we have a condition of equality, general equality in some form or another. But those conditions of equality will take probably one of these four forms. Either the distance traveled by one vehicle is equal to the distance traveled by the other, or the distance traveled upstream is equal to the distance downstream. That'll be a general idea for building an equation. Now, from that point, we think, well, distance is rate times time. So this is some rate times time, and that's some rate times time. We fill in, and away we go. Another overall concept for solution is that time is equal to time. Another is that distance plus distance equals total distance, or time plus time is total time. So we're kind of looking for one of those overall general ideas in these kinds of problems. Sometimes there'll be more than one of these available to us, and we can solve the problem in a couple of different ways. Consider this example. Suppose a soccer team is traveling a long distance to a site where there is a soccer match, and there are a couple of cars, and one is faster than the other. The slow car leaves first, the fast car leaves a little while later, and so we have an overtake situation here. The specifics run like this. The first car travels at 48 miles per hour. The second car leaves a half hour later and traveling at 58 miles per hour. How long will it take for the second car to overtake the first car? You know, this is the kind of problem that every now and then you hear on late night talk shows. One of the hosts will mention a problem like this just in joking. And it's funny because it isn't realistic. And because we don't solve problems like this day to day. And they're right, it is kind of comical to think that we would have to solve this day to day. That's not the point here, though. It's not the point that we think that we're going to, in one day, have to solve problems like this for a living. That's not the idea. It's the notion that we're developing a skill to organize a problem such as this, because it turns out that the skill that we learn in dealing with problems like this will transfer over to other problems that do have a more realistic, real-life application. Well, let's get back to the problem. Now, since two vehicles are involved, we might just begin our thinking by setting up a table of information. And while we're setting it up, we might be thinking, well, what is a prevailing condition of equality in this problem? What's equal here in terms of like distance, rate, and time? Well, we could think this way. We could think, well, we have a fast car and a slow car. I'll just put fast and slow here to label the cars. And in overtake problems, it turns out that the easy way to work this is to think about the distances being the same. After all, they're leaving from the same point. The two cars leave from the same point. And once the fast car overtakes the first one, they have traveled exactly the same distance and the problem is over. So we can think then that our general concept for solution will be distance is equal to distance. And we can kind of indicate that like this with an equal sign going this way to tell us how we're going to structure our overall concept for solution. Okay, now we just need to label rate and time for both the fast and slow cars. Well, the rate is pretty straightforward. The fast car is going 58 miles an hour, and the slow car is going 48. Now, the times need to be represented according to the idea that this faster car is leaving 1/2 hour later. So there is this condition where whichever one we let a letter stand for, there is a difference in a half an hour for the other one. And it doesn't make any difference in the overall solution to the problem which one we let a single letter stand for. Now here's what I'm talking about. I'm just going to let T stand for the time associated with the slow car. All right, so if T stands for the time for the slow car, now the fast car is leaving a half hour later than this one. So it's traveling for less time. So the time associated with the fast car is t minus 1/2. Now, once we finish with this problem, though, we're going to look at t, and we're going to say, what's t stand for? Well, t stood for the time for the slow car. Is that what we're looking for here in this problem? We're going to discover, no, it's not, because it says, how long will it take for the second car to overtake the first car? So our time clock starts when the second car leaves, not when the first one leaves. But yet we're finding the time for the slower car, the first car that's leaving. Now this sounds really complicated, but the point of this matter is, in this labeling process, you should not worry about whether you are labeling something with a single letter that is precisely what you're looking for in the problem. That's one of the situations that occurs in problems like this, that a lot of times you just start your thinking about some unknown quantity that you can solve for. But at the end of the problem, you come back and you go through and you sort of analyze it and say, have I really solved the problem? If not, then whatever it is that you solved for will help you find what you need. You see, that's the idea. So don't worry about it at this point in the problem. Worry about it at the end. All right, let's run through it. We have, let's see, the distances are equal. So our concept is that the distance traveled by the fast car is equal to the distance traveled by the slow car. Distance equals distance, you see. Okay, now what is distance? Well, distance is some rate times time, and this distance is also some rate times time. So for the fast car, the rate is 58, and the time, 58. And the time is t minus 1/2. And then for the slow car, the rate is 48, and the time is t. All right, and we go through and solve. Let's see, 58 times t is 58t. 58 times minus 1/2 is minus, let's see, half of 58 would be 29. And then this is equal to 48t. I'm going to kick my variables over to this side. Let's come out over here to finish this out. I need a little more room. So we have, let's see, I've got, I'll just repeat the step that I have down there. I have 58t minus 29 equals 48t. I'm going to kick the variables over here. 58t minus 48t equals, and I'm doing this by subtracting 48t on both sides. That's what I'm doing. And, oops, I left out the 29. Boy, this looks ragged. All right. I'm taking 58t minus 29 and I'm subtracting 48t. That's what's happening. Now, and I'm subtracting 48t over here. When I perform the subtraction here, I get 10t minus 29 equals 0. And now I add 29 on both sides to clear this, so I'll have 10t equals 29. You might be saying, why didn't I just put the terms involving t over here? Well, it's because they would be negative and I would divide by a negative, and I don't know, I'm just a little more comfortable doing it this way. But it really doesn't make any difference. When I divide on both sides by 10, or divide over here by 10, I get t. Divide over here by 10, I get 29 over 10, which is 2.9. Now, that's 2.9. T is, well, let's see, my unit for rate was miles per hour, so the unit of time is hours. So it's 2.9 hours. Now, is this what I need? Well, let's go back and to see. We would see, okay, I found t to be 2.9 hours, but t is the time associated with a slow car. This is that little discussion we went through before. And that's not really what we want over here, because we're asked how long will it take the second car, the fast one, to overtake the first car. So we want the time associated with the fast car. Now, the fast car's time is t minus 1/2. If t is 2.9, then it's 2.9 minus 0.5. That's 2.4. So the fast car's time is 2.4 hours. It'll take 2.4 hours for the fast car to overtake the first. Here's another problem. Now, this one we're going to look at in two ways. And this problem is, well, I've chosen one that's a little bit difficult because I want to make sure that you don't encounter any that are any more difficult than the ones that I show you here. If you can do these and understand these, you'll understand all of the ones that you bump into. All right, here's the problem. It says, two cars start at a given point and travel in the same direction at average speeds of 30 and 45 miles per hour. How long will it take for the cars to be 5 miles apart? Now, in the previous problem, they started at a different time and one overtook another. Now they start at the same moment, and we want the time when they are so many miles apart. But the idea is pretty much the same. That is, we can easily structure an overall condition of equality. In fact, there are two of them here that we're going to look at. Because it turns out that with problems like this, there are maybe 2 or 3 ways to solve it correctly. And if you do it one way and you see me do it another way, you might think that your way is wrong. It's not. There are all the roads lead to Rome here in this situation. Okay. We start with the table of information, slow car, fast car. All right, distance, rate, and time. Now, it might occur to us at the very beginning of this that, gee, we have a difference in the distances as 5 miles apart. So we might think, wow, that's our overall concept for a solution, that the distance traveled by the fast car, because it's going farther, you see, it'll go farther because it's faster, minus the distance traveled by the slow car is equal to this 5 miles. Difference in distances is equal to 5 miles. And now, this is a rate times time, this is a rate times time, and away we go. Somebody else might say, well, wait a second. They leave at the same time, and at the moment that they are 5 miles apart, the problem's over. So they're traveling for the same amount of time. So somebody else might say, well, time is equal to time, and we might set it up like this. Time traveled by the fast car is equal to the time traveled by the slow car. So we have a distance divided by rate. Time is distance divided by rate here for each of these. So we have a d over r here, a d over r here, and all we need to do is represent them in our table of information. You see, so if we think about the concept for a solution, it might lead us to begin to structure the table in a particular way. That is, the table would come after the concept for a solution. Sometimes the table comes before, sometimes it comes after. It's just whatever kind of occurs to you. Now, for the slow car, let's put in what we absolutely know in the problem. We know that one car travels 30 miles an hour, the slow car, and the other travels 45 miles an hour. All right, that's pretty straightforward. Now, if we're thinking about this difference in distance idea, then we need to, and this distance is some rate times time, and this distance is some rate times time, then we need some representation for rate and time. It's the time that we're concentrating on in order to deal with this. Okay, let's do that. Let's see, we have, how long will it take for the 2 cars to be 5 miles apart? Oh, the times are the same. So this is a t and that's a t. Okay, that's good. That's great, because then this is just, let's see, the fast car is going 45 miles an hour. And for t number of hours, we don't know what it is, but that's what we're solving for. And the rate for the slow car is 30 miles an hour, and the time is t. Oh, this is easy. We have 45 minus 30, that's 15t equals 5. Dividing on both sides by 15, let's see, over here we would get t, and over here we would get 5 over 15, and I'm about to run out of room at the bottom of the board, but this is 1/3, and that's 1/3 of an hour. You see, so that's nothing more than 20 minutes. So it takes 20 minutes then for the cars to be 5 miles apart. That's really simple. Now, what if it had occurred to us to think about the problem in terms of time equals time? You see, and this is another one of those situations where I'm not really worried about whether I'm solving for the thing that I'm looking for. Although I'm looking for how long will it take, I'm looking for time in this problem. If I ignore that idea, then I might jump into this kind of solution. I might say, okay, the time associated with the fast car is equal to the time associated with the slow car. Now, that's distance over rate, distance over rate. Now, what about those distances? Well, gee, we can represent those distances in our table of information. Let's see, if the distance traveled by the slow car is x miles, then the distance traveled by the fast car is, well, let's see, we're talking about the cars being 5 miles apart. So the fast car is going to go 5 miles farther. So this would be x plus 5. Now, if I had represented the fast car's distance as x, then the slow car would go 5 miles less than that, so this would be x minus 5. So there are a lot of ways of setting it up correctly. But representing it like this allows us to pop in the information in this d over r format. So let's see, the distance traveled by the fast car is x plus 5, and its rate is 45. So we have x plus 5 over 45. On the other side, distance over rate is x over 30, x over 30. Now we cross multiply x times 45, 45x, and then going this way, 30 times x plus 5 is 30x plus 150. Subtract 30x on both sides, we get 15x equals 150, x then is 10 miles when we divide by 15 on both sides. Now, is x what we're looking for in the problem? No, it's not, but let's use it to find out what we need. Let's see, if x is 10 miles, this is x, 10 miles, it's a distance, but we're looking for the time here. And once we discover that we didn't find what we're looking for, then all we do is say, well, how can we find the time? Well, we know the distance traveled by the slow car is 10 miles. We know the rate is 30. Gee, that's pretty easy. We can just come out here to the side and say distance is rate times time. The distance of 10 miles and a rate of 30 allows us to solve for time. Divide by 30 on both sides, and we get this. So time then is 1/3, or that's 1/3 of an hour, which is 20 minutes. So in 20 minutes, the cars will be 5 miles apart. Let's turn our attention now to combined work problems, sometimes called work rate types of problems. That kind of problem would be like this. Suppose we had a couple of tractors. We have an older tractor, and the older tractor can plow a field in, say, 6 hours, and a newer tractor only takes 4 hours to plow the field. We could figure out how long it would take to plow the field if the two tractors were working together. In a more urban kind of example, we might think about, okay, we have a print shop, and the print shop has old printers and new printers, and an old printer requires so much time to print a job, and a new printer requires so much time to print a job. How long would it take for them working together to print this job? Well, let's just take an example. There are really two ways to set up problems like this, and I'll show you both ways. This one says Sue can paint a room in 4 hours, Beth can paint the same room in 5 hours. How long would it take to paint the room if they worked together? Now, Sue's time is 4 hours, Beth's time is 5 hours, and we're going to say that the together time is X number of hours. One way to think about structuring a mathematical model for this is to consider what's going on in 1 unit of time. What fraction of the job can be accomplished by Sue working alone, Beth working alone, and what fraction of the job is accomplished when they work together? So if we're thinking about it like that, then we would begin our thought process like this. If Sue requires 4 hours to paint the whole room, then what fraction of the room can she paint in 1 hour? Well, in 1 hour, she's painting 1/4 of the room, you see. And for Beth, if Beth takes 5 hours to paint the whole room, then in 1 hour, she's painting 1/5 of the room. So it truly is the idea that the fraction or the part of the job that each of these people is accomplishing in 1 hour, in 1 unit of time, is the reciprocal of that total time. So if together it's taking X number of hours for them to paint this room, then in 1 hour they are accomplishing this part of the job. All right, that's a very important idea. If this were 15 hours, then in 1 hour they would get 1/15 of the job done. 15 is unrealistic here, because certainly if it takes one of them 4 hours and one 5, it's going to take less than either of these times for them to accomplish the job working together. But at any rate, that's the idea. We need these fractions involved in order to structure our equation. In 1 hour, the part done by Sue, which is 1/4 of the job, plus the part done by Beth, which is 1/5 of the job, is equal to the part that they accomplish working together, which is this fraction of the job. You see, and then we go about solving that equation. Let's talk about the concept for solving the equation using another idea. The other idea is this. It really specifies work rate as part of the problem. It's like this. The entire job The accomplishment of this entire job is equal to the portion of that entire job accomplished by Sue plus the portion of that entire job accomplished by Beth. Now, the part done by Sue is found by taking the rate at which she works times the time. It's a rate times time idea. You see, her rate times time, and then the part done by Beth is her work rate times time. Now, the time it takes them is the unknown quantity here. It's just like an unknown like t. And the job is just one job. The entire job, one job. Okay, one job is equal to, now the work rate for Sue is 1/4 of the job per hour. So 1/4 of the job per hour times t number of hours would be the part that she accomplishes. And the part accomplished by Beth would be her work rate times the amount of time required. And then we solve this. Well, I'm pretty confident that we can solve either one of these. I'm going to go through the first one, though, the first setup, because it is not one that's illustrated in the textbook. This method is illustrated in the text. The method for solving this equation, now this is the idea that this is the fraction of the job that's accomplished in 1 hour by Sue. This is the fraction of the job that's accomplished by Beth in 1 hour. This is the fraction that they accomplish working together in 1 hour. All right, now we have an equation involving fractions. We identify a common denominator. The common denominator is, let's see, 20 for 4 and 5, and then we tack on an x factor. So 20x is the common denominator. We multiply 20x times each one of these, and we get, well, let's see, we have 4 into 4, 1, 4 into 25. This becomes 5x. And then the 5 and the 20 cancel, leaving 4. This is 4x times 1, or 4x. And over here, the x's cancel. 20 times 1 is 20. 5x and 4x, 9x, divided by 9 on both sides, we find x to be 20 over 9. So x, the amount of time required if they work together, is 2 2/9 hours. I'm sure we've noticed in this section so far that some of the problems we encounter have formulas associated with them. They're kind of built into the nature of the problem. If we're talking about interest problems, then interest is principal times rate times time. If we're talking about distance problems, then distance is rate times time. And we then build variations on those themes. Well, if we're talking about geometric figures, the same idea holds true. That is, if we're talking about rectangles and triangles and so forth, then there are formulas associated with them for calculating perimeter area. And if they're three-dimensional figures, then we're talking about volume. But here's an example from that kind of problem, and the formulas are written in your textbook, and I invite you to take a look at them. We can refer to them in settling a problem like this. Suppose we have a house on a lot, and we know that the lot is 250 feet long. Suppose we also know that the area of that lot is 30,000 square feet, and we'd like to calculate the width. Well, we calculate the width by using a formula that relates the area of this rectangular piece of property. And the area of a rectangle is calculated as multiplying length times width. Now at this point, as soon as we write down the formula as our mathematical model for a solution, we really have two ways to approach the problem. We can actually take the formula as we see it and solve it for W. That is, we would divide on both sides by L, and we would get A over L equals W, and then fill in for area and length, you see, to finish out the problem. Another way is to simply take the formula as we see it and pop in the letters that we know information about, and then go from there. And I kind of like that approach. Area we know to be 30,000. Length we know to be 250. And now we're solving for W. To isolate W, we divide on both sides by 250. So we have 30,000 divided by 250 on the left, and on the right, the 250s would cancel, and we're left with W. Here, when we divide, we find that quotient to be 120. So the width then is 120 feet. And we can then put 120 feet here. Now let's complicate matters a little bit. Let's consider that the city is putting in a sidewalk. If the city puts in a sidewalk and charges $1.50 per foot, how much will you pay if you have a corner lot? $1.50 per foot. Now this is $1.50 of linear foot. We're not talking about the area of the sidewalk here. We could be talking about that. We kind of have to know how wide the sidewalk is and we can find its area. That would be more complicated still. But this has only to do with the measurement of the length and width of our corner lot. It's this idea that if we have a corner lot, and let's just make it this corner that we're going to put that the sidewalk is going to make its appearance on. Okay, so there's the sidewalk. And the city charges according to the number of linear feet of your property to which it is attaching the sidewalk. So it's attaching the sidewalk along this side of the property and that side. So we're just going to add these two to get the total linear footage. But how do we calculate the total cost? Well, the cost, you know, is calculated as, now here, notice that I'm starting to build a mathematical model for solution, and that model doesn't have a formula associated with it. I'm just doing it by the nature of the problem. The total cost is, let's see, the length of the sidewalk times the cost per foot. Or the rate of the charge rate, you see, that is associated with this. Okay, so that cost then is, well, let's see, the length of the sidewalk, we're on a corner lot, so we have to add the length and the width together of our lot. I'm looking over here, 250 feet for the length, 120 for the width, 250 plus 120, that's 370, so we have 370 feet of property on which the sidewalk is to be attached, and the cost per foot is $1.50. Multiplying, we find that cost to be $500.